Alright, hello everyone. So this is the first lecture for Chem 1151 Survey of Chemistry at Columbus State University. I'm John Geary. I'll be the professor for this course. My course is entirely online, so everything that you will need will come from either ALEKS or CougarView. Okay, so make sure that you've looked at the intro video and that you have gotten registered for ALEKS and are ready to get started on uh, the ALEKS Mastering Chemistry program. Okay, so today we're just going to do an introduction of the things that you'll need for this course and where to find information, content, uh, resources, stuff like that. And then we'll also get started on Chapter 1, Matter and Measurement. All right. So just to kind of make a note, this is a video I'm trying to make ubiquitous, meaning that every teacher can use it for students that may not be able to come into class this week due to COVID or other reasons. So I'm going to refer to my course for dates and assignments and stuff, but if you're in another teacher's course, you want to make sure that the assignments and dates are that you understand when those assignments are due and that those times might be different than the ones that I'm saying. Okay, but other than that, all the materials should be the same, and you should be going through very similar things with ALEKS and CougarView. Okay, so that being said, let's go ahead and get into all the introductory stuff, and then we can get started on learning chemistry. Alright, so this is CougarView. This is the home page for the Survey of Chemistry course. This is the fall semester 2021. You'll see on the home page announcements. These are where I will communicate with the course the most. Okay, so check in every couple days or so and just make sure that I haven't put up a new announcement or made some changes or something like that. Anything that I pretty much do, I'll make an announcement here. Okay, so those of you that were having problems signing up to ALEKS or paying for your access code, I have gotten temporary access codes from ALEKS, the ALEKS support staff. Follow these instructions. Use this financial aid access code. This will give you 14 days in the program, so enough time to kind of get started, obviously, but also enough time for them to get their bugs fixed and allow you to pay for access to the course and the text or whatever. So for those of you that were getting hung up there, I've done that. And then everything else that you will need, like I said, these are just announcements. This is kind of how I'll communicate everything. But most of your content and supplemental videos will be under content. Okay. Now there are no assignments necessarily for CougarView. All of your assignments for the lecture course should be completed in ALEKS. That might not be true for other teachers. They may do quizzes and stuff or worksheets that would be due in CougarView. If that's the case, it would be under assessments, assignments, or quizzes probably. I will probably do the exams here. But ALEKS also offers all of these options on its website as well, so your teacher may choose to do something else. Now, for getting started, for my course, I did a getting started section. Watch that intro. Make sure that you're registered to ALEKS. Look over the syllabus. Make sure you understand where your grades are going to come from, and that's pretty much all you needed to do for getting started. Now, for Chapter 1, I kind of set up like every chapter is going to be set up. I will provide PowerPoints, okay, provided to me from the McGraw-Hill people. And then I'll also do like little supplemental videos. My lecture, of course, will be posted here as well. I'll probably put that at the top. And then these other links are not required, okay? These are just kind of supplemental resources that help you in case you run into problems or get hung up on a specific subject or topic. Okay, use these videos when you're going through ALEKS or before you even go through ALEKS. If something didn't quite gel or make sense, check out these YouTube videos. Go on to YouTube, find some of your own videos, somebody that you can relate to and learn from, because we all have different learning styles, right? We all absorb information differently. Some of us are math minded, and some of us are concept oriented, so it's hard to teach something in a way that everybody gets immediately. So I like to provide videos that are different from my teaching style and that explain things either more thoroughly or in a different way, and then hopefully there's something for everyone, right? There shouldn't be any reason why all of you can't understand the content of this course. And so I try to provide as many different avenues as possible to kind of get you where you need to be, if that makes any sense. All right. So like I said, you don't have to look at these. They're just there to help in case you start getting hung up. All right. So the last thing I want to do for the introduction stuff is kind of go through ALEKS and talk about it. So once you get registered for ALEKS, it will take you in to a program like this. My screen will look much different than yours, so that's how come I have to do all this to get there. Alright, so it'll open up like this and it'll take you through a few different tutorials. I recommend you go ahead and do these just because well, some of you may have not ever used a program like this. If you have used Master in Chemistry or Master in Physics or something like that before, it'll be very similar to that, but ALEKS is different and kind of does their own thing. So I recommend doing all the tutorials anyway. I'm going to skip that. Another tutorial, how to use the program, how to type in answers, how to check yourself. I'm going to skip that as well. Sorry. I recommend you do all this. Alright. So, then, once you get done with your tutorials, you will come to what's called a knowledge check. The knowledge check is going to kind of assess where you stand at right now before we get started learning anything. Okay, so go ahead and do your knowledge check. If you do well on it, I think it can give you up to 10% of your final PI already completed, so you'll have 10% less work to do for the rest of the semester. Okay, if you don't know anything, I think there's an option is to say I don't know. That's fine too. If you want to kind of pretend like you're starting from bare scratch, then that's fine. You can kind of skip through the knowledge check, and then you'll just have to complete all of the topics as they come up. But try to do your best. I recommend trying to go ahead and do your best. It couldn't hurt, and then you might know more than you think you do. If you think you know a lot, you might know less than you think you did. So the knowledge check is going to be a good indicator of where you stand at coming into this course. Okay? So let me do that, skip, and it'll do more tutorials, blah, 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 start, question. Now I'm going to skip knowledge check. I'm going to act like I have zero knowledge. Okay? Now, this is your total PI. Mine says 10%, not because of the knowledge check I just did, but because I went ahead and went through the topics that you have due next Sunday. I went ahead and went through and just did them to kind of get a gauge for how long everything would take. It took me, obviously knowing this material very well, it only took me about 30 minutes to get through all 11 topics. Okay, so I would recommend that you go ahead and learn the material before you get started on the objectives, just so that you don't miss as many, right? If you know it before you come into this, if you kind of have a good feeling for how to answer the questions in the first place, then you're going to be much better off when you get started doing the objective. Because if you miss an objective, let me get into that and kind of show you what happens there. Continue, start, No. Assignments. So I've already done this one, but I'm going to go back in and act like I haven't. So this is kind of the intro. It'll tell you what this section is learning. So this is the value of an SI prefix as a power of 10. Okay? And we'll talk about this here in just a minute. I'm going to get started on this in the lecture. But I want to explain to you how the ALEKS program works so that you know what to expect when you get here. Alright, so I'm going to start this. Now all of these questions will be different for everybody. I think they're generated randomly. So I'm going to go through and answer them. And then mega. Alright, so I'm just entering the prefix or the exponent for the given prefix. Alright, and so you'll see here at the top right, let me make sure y'all can see what I see. Okay, at the top right, I just got a little green bar for answering that correctly. If I answer the next one correctly, it'll give me 2 more bars, so kind of double the credit for that. Deci is 2. Actually, minus 1. And that's a kilo. And that's a centi. Alright. So you see there, I got 2 bars for that one. So I got double credit. Alright, now let's keep going. If I answer this next one correctly, that's it. I'm done with this topic, and it'll give me 100% for that topic. Now what I'm going to do here is I'm going to miss one on purpose. So let's just say that's 1, that's S. These are obviously incorrect answers. Okay. Okay, so you see I lost one there. Alright. If I lose, let's say I do it again, recheck. Okay, so now it gives me an explanation. Alright, and it'll kind of tell me, what I should be doing, how I should be answering these, give me examples of different problems or whatever that I might see. Like this is the exact same thing they're asking me. They're giving me examples of how I should answer it. So, do the best you can. Make sure, try to double check yourself and make sure that you have your answers right. The more that you get correct in a row, the quicker you get done with the mastery portion of ALEKS. Okay? And if you start missing 1 or 2 in a row, first thing it'll do is try to help you. And then after a certain number of misses, you'll essentially get a lower percentage for that topic. Okay? You can still go back in and review it, but your grade for that topic will be 50% or something. So try to understand the material before you get started on the ALEKS program. Okay, now another thing I want to point out in here is your textbook. Your textbook is available in ALEKS. So most of you, when you bought your access code, you also bought access to an ebook. I've just opened it up. I have to switch it on my other screen though. Give me just a second. Alright, so now when I click on ebook, it opens up another box with my text in it. So this is your text. Let me go back to the main page. Where's the cover at? Okay, there it is. So this is what your text should look like. When you log into ALEKS, there might be a little picture of this. I think you can just click on that and it'll take you straight to your text. Okay, you can open up the contents page and kind of scroll through. I also have a physical copy, but I'll just go ahead and tell you it's written just like this. So this is actually much easier to deal with because my text looks like they wrote a computer program, printed everything off, and then stuck it in a book. Alright, it looks like it was designed for an ebook, and so that's what I feel is the easiest way to move around in it. Alright, and so then this will have everything All the material that you're going to be tested on in ALEKS is in here. You can find links from ALEKS to these topics by clicking on there and just scrolling through and finding the section that you need to kind of review or whatever. Alright? So, if you have any questions about ALEKS, about how that works, about how CougarView works, you can email me. If you start getting hung up while you're doing the ALEKS stuff, you can screenshot your problem that you're working on, send it to me with your answers or whatever, and say, hey, how come I got this wrong? And I can say, well, you forgot to account for this, or maybe you didn't understand this certain part of it. I can either do little private videos, like where I can just kind of go over your problem that you're having, or I can provide more links to supplemental videos that will help you kind of get through it. Okay? So, I think that's all I'm going to do for the introductory stuff. Like I said, you can email me and let me know if you have any problems, or if you didn't understand something there, if you're still having a problem with the ALEKS program, or whatever. Okay, email me if you feel frustrated and can't figure it out. I will try to help whatever way I can. Alright, so with that being said, let's get into the lecture. I'm going to split up chapter 1 into 2 parts. Today we'll cover up to section 1.4, measurements, and then starting next week we'll start at 1.5, significant figures. Okay, so I'm going to go to the PowerPoints. I like them better. It doesn't have too much extra material, and I can just kind of lightly go over things. Most of this should be somewhat familiar to you. Most of these are terms that we use in everyday life, and has stuff that we start learning from a very young age. Chemistry, for example. You might not have studied chemistry until the 9th or 10th grade, but you kind of had an idea of what chemistry was probably very early on. So technically, chemistry is the study of matter, its composition, properties, and transformations. Now, in order to understand that definition, you have to understand what matter is. Okay, and that's the biggie. Matter is everything that takes up space and has mass. Now, this can be kind of tricky, okay, because we think about the air, right? The air, it obviously takes up space, but does it have weight? Does it have mass? It absolutely does. It's just so light that it floats, right? So, and it's all gas, so they're all floating and bouncing around up in space, up into the atmosphere, gets thinner and thinner and thinner. But all of those little particles have weight. If I could measure a jar without any air in it versus a jar with air in it, you'll find that the jar has slightly more mass than the jar with no air in it. Okay? So air is matter. Okay? Oxygen, nitrogen, carbon dioxide, all of these are chemicals, gaseous chemicals that are floating around in the air, and they have mass. Some examples of things that do not have mass would be like the wind, right? The wind is an energy, it's a force that's moving air around, but the wind itself is not made of anything heavy. There's no weight to wind. Sunlight is another example. There's no necessarily weight to sunlight. It's rays, electromagnetic waves moving through the air. They have energy, but not mass. Okay, so sunlight's not matter, wind's not matter, stuff like that. Okay, so let me get back on here. All right. And then I also recommend going back to your text though and reading. Let me show you what the text has real quick before I keep going. So it has like the figures and health related topics and stuff like that. I like reading all that because it relates the information that you just learned to something in the real world. Okay, and for me, that's the best way for me to kind of learn. And when I think about something, I think about the example of that thing. And you'll notice when I teach, I do a lot of examples. For instance, this, I just did the jar of air versus jar of no air, right? I'll do a lot of real world kind of things like that because that was the way that I found it was easiest for me to learn. So reading these topics in your text, kind of relating the information that you're taking in with real world topics, I think is amazing and really helps to, you know, embed that information in your brain. Okay, you absorb it faster, and you can always come back to it because you remember that example. You know, so I definitely recommend reading the little tidbits from each section. Okay, so all right, so now for the states of matter, everybody's heard this before, right? Solid, liquid, gas. Now we're going to kind of analyze what they mean on a chemical level, but most of you are familiar with this, right? Solid is like a little box, right? We like to think about little boxes. A liquid would be like a water, glass of water or something like that. And then gas, obviously the air. We were just talking about the air. So that's the three examples I'm going to use. Let me go back to the slides though and kind of explain each one individually. So now let's talk about the box, right? This is just one real world example, but I'm going to talk about it as a box. So the solid box, it maintains its shape regardless of its container. What that means is if I throw the box in a jar, it doesn't just crumble down to the bottom of the jar and fill it up like sand, right? Even though sand is a solid, the particles are so small it kind of moves around like it might be a liquid, right? So that's why I want to kind of illustrate that in the glass. So a solid maintains its shape regardless of its container, has a definite volume, so it doesn't expand and contract, that's what that means, and the particles are tighter to each other in a regular pattern. Okay, so the particles part might not mean much to you just yet. Let's look at liquid and talk about how that's different than the solid. Okay, so liquid has a definite volume. It doesn't expand and contract, right? But it takes the shape of the container. So make sure y'all can still see me. Let's go back to the glass of water versus the box. Okay, when I took the box and I threw it in a glass, the box just kind of sat up there like a chunk of ice, right at the top of the glass, couldn't even fall all the way down. It kept its shape regardless of the container. All right, now for water, that's not the case. It fills that glass up. All right, it fills all the bottom up and it just keeps stacking up on top of each other and it keeps changing its shape. If I were to move that through a straw or something, the water would change its shape again. It'd get tighter until it got up through the straw, and then it'd be in a long, cylinder type shape. So the liquid changes to adapt to the container that it's in. Now you have to be careful about thinking about the size of these things, okay? Because like I was talking about sand. Sand, if you think about it, technically I could fill it in, I could pour it into a glass or whatever, and it would fill the shape of its container. But that individual sand particle would not, right? That individual little piece of sand is solid. It doesn't change its shape. It's essentially like a mini box, right? It's a box still, but it's so tiny that if I get, 3 million boxes, 3 million tiny boxes, I can kind of maneuver them and make them do things as a whole, but not individually. So it's kind of a size relative thing you got to think about, but solid, liquid, and now gas. A gas does not have a definite shape and it does not have a definite volume. So what that means is that I was talking about expanding and compressing. If I expand, now volume is what takes up the space. Volume is just a space. So like a pool, for example, is filled up by a volume of water, three-dimensional volume of water. If it were all water, right, and I filled up that pool, I couldn't press it down anymore, right? Water can really only get compressed so much and it'll just push back. So it has a definite volume. Doesn't matter how much I press on that or try to expand it, the water is going to take up the same amount of space. If that were a solid, it would do the same thing. I could press on it, probably wouldn't even press down any. You know, water I could press on, but it ended up pressing back. The solid might not press down at all. If it was metal, you know, and not enough force, I couldn't even press down on it. So the volume stays the same. Now with the gas, that's not the case. With a gas, I can compress it. Okay, these particles are very loosely, you know, in this environment. Okay, and that's why it shows these pictures of some particles. These are kind of moving around each other. The solid particles are fixed. They don't move at all. They're connected in certain ways and they don't move. But the gas is not connected. They're not close to each other even. So if I go to start compressing that, if I have a pool full of gas and I can find a way to compress from the top, I can smash all of those particles down into a volume about this size, you know, smaller than a baseball or something. And that's all of the gas that filled that whole pool at the beginning. I have down into a little cylinder, you know, and that's how we compress our gas and put them in these little cylinders to send out to stores or whatever. So gas does not have a definite volume. It does not have a definite shape. It fills the entire room that it's in, or the entire container that it's in. It just keeps expanding, expanding, expanding. Right? You think about space, the air. It keeps expanding till it gets there to that outer shell, and then it's so thin, and it just gets thinner. It doesn't even really stop. It just gets thinner and thinner and thinner until eventually there's nothing. All right. So that's the three biggest points are highlighted in these slides, though. Definite volume fills the shape of its container or doesn't, and how close the particles are to each other and whether or not they're fixed. Okay, solid has fixed particles. Gas are just random, essentially. Okay, so now let's talk about physical properties of matter. So the physical properties are things that are just, they kind of tell us what can be observed or measured without changing the composition of the material. So a chemical, I'd rather do this versus rather than just explain one. So a chemical property versus a physical property. And I've also included a video in your Cougar View for this. So physical properties are properties that if they change are not changing the chemical nature of the matter that we're talking about. Okay, so boiling point, melting point, solubility, color, odor, states the state of matter, so whether or not it's a liquid, solid, gas. And let me kind of touch on that just so you kind of understand what I'm saying. The boiling point of water, which by the way is when I change from a liquid to a gas. Okay, when I'm boiling a pot of water, I have a pot of liquid. I'm going to raise the temperature so much that that liquid will become a gas and start to boil away, steam off, right? So what's happening there is a physical change. It is changing the states of matter, and it is indicated by the boiling point. So because the boiling point reflects a change in the state of matter, it is a physical property. Okay. The melting point is the same thing. It is a change in state between solid and liquid, right? Once the ice begins to melt, it stops being a solid and it becomes a liquid. That is a physical change, thus the melting point is a physical property. All right? And the same can essentially be said for all of this. Now, a physical change alters the material without changing its composition. When I went from ice to water, the individual water molecules are still the same. It's still two hydrogens and still an oxygen. but the way they're arranged is different, right? When I was in the ice form, they were rigid and connected and stable and didn't move, and so they were like the solid, right? The particles lie close together in a regular pattern. That's what I meant by connected and stable. All right. Once it became a water, the particles were still close to each other, but it kind of allowed them to start moving around and sliding around each other, kind of rotating and doing all these different things that it wasn't able to do with the ice. So now it's a liquid and it's moving. And that is, those are both the physical properties of water. The boiling point is 100 degrees Celsius. The melting point is 0 degrees Celsius. Was it 32 Fahrenheit, 212 Fahrenheit for those respectively? Okay, so that's how you kind of identify a physical change, whether or not it changes the actual composition of the the chemical or the compound that we're talking about. Now, the chemical properties and chemical changes uh, converts one substance into another one. So the water molecules are no longer water molecules. They've been split up into hydrogen atoms and oxygen atoms. Okay, so that was a chemical change that occurred. Now, chemical changes can be detected by several different things, and we'll talk about this more in lab when we get there. But giving off an odor is one, and that's why this was kind of confusing to me. I wouldn't the nat so let me explain why it says color and odor here. The color that something has is a physical property. The odor that something has is a physical property. Take sulfur, for example, sulfide that we find in eggs and stuff like that. Okay, that has a particular smell. How I would know that is the physical property of the sulfur, but if I were to go through a reaction of some sort and that odor is no longer there, I can assume that I have changed uh, the chemical properties of that. Okay? Same with the color. If I change the color of something, I can assume that I've changed the chemical nature of that compound because the color and the odor was a physical property specifically associated with this chemical, and now it's different. Okay, so if you see a color change, that's an indication of a chemical change. If you notice odor arises or goes away, that should be an indication of a chemical change. Another thing that might indicate a chemical change is heat. Right, if some type of energy is given off, whether it be an explosion, fire, some things like neutralization reactions will just get real hot, and you can feel it on the test tube when you're doing these reactions. Okay, some get so hot they can burst the glass from the inside. So it's really cool to sit there and do all those things, but what you're really trying to look for is whether or not it was a chemical change or a physical change, and thus whether it was a chemical or physical property. Okay? So let's talk about how we classify matter, how we distinguish between compounds and mixtures. A pure substance is composed of only a single component, so either a certain type of atom or molecule, and it's all the same thing. There's no, salts thrown in there or little particles of anything else. A pure substance is all one single thing. So water is, if it has nothing else in it, will be a pure substance. Some things are not just individual. So let me come back to this little illustration here. Notice that hydrogens come in sets of twos. So does oxygen. Oxygen comes in sets of twos. So those, if I had a can of oxygen, they'll all be double, O2 molecules, but it is a pure substance because it's all the same. Okay? Now, pure substances, so it has a constant composition regardless of sample size or origin of sample. So if I got a glass of something and I stick my hand into any portion of the glass and pull out a handful of it, it would be the same as if I stuck my hand in again and pulled out any other portion of it. That's how you know kind of it's a pure substance. If I see anything else in there, say I'm looking at a clear liquid, but there's little black specks in there floating around, it's obviously not a pure substance. Okay, there's something else in there. If it was pure, all of it would be a clear liquid. Okay, so little things like that are just instant indicators that this is not a pure substance. All right, a pure substance cannot be broken down to other pure substances by a physical change. They have to be changed chemically. Okay, now a mixture is composed of more than one component. So the glass with the black flakes floating around, that would be a mixture. A bowl of cereal is a mixture. Even a glass of sweet tea essentially can be a mixture, or it can be. We'll come back to the sweet tea when I talk about homogeneous versus heterogeneous, because there's also the same thing that we were talking about with solid and liquid and gas and stuff. There can be little variations. I said that the sand is a solid, but it can get so small that I can have millions of them and it can still move like a liquid kind of. So there's also little nuances like that for mixtures I'll come to in just a minute. So a mixture are composed of more than one component. They can have varying composition. Any combination of solid, liquid, gas. So that's why I was talking about a bowl of cereal has chunks of solid in there, and it has the milk, which is a liquid. So it's a mixture, obviously, because there's two different physical properties that you see. Okay, so that was a dead giveaway. The same with the black flakes floating around in water. One's a solid, one's a liquid. It has to be a mixture. Everything else is not as obvious, right? Mixtures can be separated into their components by a physical process. So one that just kind of comes to mind is oil and water. So oil and water, we know, doesn't really mix. The oil will sit on top of the water. Now I can do something, I can shake it up really hard and have a little enough oil in there where it might not matter, and I can shake it up a lot. Soap is another example. Soap and water kind of will say separated until you start to mix it all up, and then it creates all them bubbles. So anyway, I can mix it up and get the oil and water to kind of combine for a little while, but then I can go through a very simple process of just letting it sit, or maybe filtering out the water. All different kind of ways that I could separate those physical processes, that I could separate the oil and the water back into two different components. So like I said, it's not always so obvious that it's a mixture. Sometimes you have to kind of use clues that tell you that something is different than the other. And when you get into your ALEKS, they'll test you on that, and they'll kind of go through some tougher problems where it'll say, I have a box. Sorry, hold on, I'm just about to close out my text. Where, say I have a box and I cut the box in half. One box weighs, when I cut the box in half, I should have the same weight on each side, right? Because that's just a physical property of it. But turns out this side weighs more than this side. So something is different in here than in there. Thus, this must be a mixture, right? It can't be a pure substance, because then these two that have the exact same volume would have the exact same weight, and they don't. So you have to use little clues like that to kind of figure out whether or not something is a mixture or a pure substance. Okay? So now it comes back to sugar dissolved in water, and that's where I was going with the sweet tea example. Let's see if they bring up. I'm still going to wait on it. So sugar dissolved in water is still a mixture. You might not can see the difference there, but we know it's there. Okay, and in fact, I could go through some physical processes where I could actually probably filter out the sugar, right? Or decaf the coffee or something like that, right? So, and these are not necessarily uh, changing the chemical composition of the coffee. I'm just removing the caffeine. So, in a sense, it was a mixture that I removed one of the substances in the mixture. Okay, so like I said, this can get a little tricky. I missed one of the Alex problems because these are kind of tricky. There's some nuance to how you kind of think about the differences in physical and chemical properties, and then also the differences in mixtures and substances, pure substances. Okay, so an element is a pure substance that cannot be broken down by a chemical change. A compound is a pure substance formed by chemically joining two or more elements. So just go back to the water one is a good example of the difference between a compound and an element. Okay, so water is a compound. It has two elements there, hydrogen and oxygen. So since it has two or more atoms, um, different atoms, it would be a compound. Okay. Now the element would be the oxygen and the hydrogen individually, but they still exist as two atoms. They're called diatomic molecules, which we'll talk about later. But they're still just the element. If I have a cylinder full of oxygen gas, they're all O2 molecules, but it's one element, and I can call that the element oxygen. Water, I can't call it the elements hydrogen and oxygen because it's not. It's just water that has a combination of hydrogens and oxygens. Okay? So elements and compounds, some examples. I'm not going to spend too much more time on this. Um, but this little chart, some of these little charts and examples are really good for you to kind of determine whether or not something is a pure substance or a mixture. If it's a pure substance, or is it an element or a compound? Okay. All right. So now we're getting into the math stuff. And so this is where I was having a little trouble with my program. Usually I have a screen sharing program that I can get on my iPad and do like a whiteboard on. But I couldn't get that working today, so I've got the Paint program pulled up. I'm going to try to use it as little as possible, but I might need to kind of show you some things in writing to get it across. So give me just a second. Figure out where that is. Okay, so that's my Paint program. Okay. All right. So for measurement, every measurement is composed of a number and a unit. Okay. Now the unit should be an indicator for what type of measurement it is. Okay. So these are the SI units for well, SI meaning International Scientific. So these are the units that every scientist essentially across the world has said, hey, let's get on the same page. Let's use the same units for these things. That way, when we're talking with each other, when we're talking with France or Russia or China, everybody's on the same page. So you'll know the English units just because we've always used feet, inches, pounds, stuff like that. But in science, we always use the SI units, the basic metric units, for all, yeah, experiments or studies, or even just when we're practicing and talking about math in general. You have to use the SI units. It is good to know how to convert though, because us being American, we'll use inches and stuff like that. And so if somebody says meter, you might not be as familiar with how big of a distance that is. So I obviously recommend that you understand like the how to convert, which we'll get into more. I wish I had my iPad for that, but we'll talk more about next week when we actually get into significant figures and everything. I'll go through and kind of do some examples of converting units and how to set those up. But for now, let's just recognize what units are and how to determine what they're measuring. Okay? So, length, mass, volume, and time. These are the most used units in science, and they are all associated with certain physical properties or physical aspects of our world, right? Time. How does time pass? It passes in seconds. Okay, seconds add up to minutes, minutes add up to hours, so on and so forth. You're familiar with those. Everybody's on the same page when it comes to time. Okay, another one would be length. So something that we may say is inches or feet. The scientific community, we all use meters, and we have different symbols that tell us whether or not it's a longer or shorter version of the meter, right? The millimeter is a shorter version of the meter. It's 1/1000th of a meter. All right, the kilometer is 1,000 meters. So they have these prefixes that allow us to adjust the base unit. That's why it says base unit there. Okay, so symbol for meter is a M. Be familiar with that. Anything that measures length should be measured in a meters. Okay, it can be the other kind of meters, centimeters, millimeters, kilometers, but it needs to be base unit meters. For weight or mass, we typically think of pounds. The scientific community SI unit is the gram. Okay, same thing as I said with meters. You can do bigger, so kilograms. I think most Europeans measure themselves by kilograms. Kilograms, if I'm going smaller, milligrams, centigram, microgram, stuff like that. Okay, volume, which is what we talked about earlier with the pool taking up space, or a gas cylinder, for example. How much gas is in this cylinder? It's 250 milliliters, or it's 50 liters. Okay, liters is the base unit, and then milli, centi, kilo are all the prefixes that makes it a kiloliter, a centiliter, whatever. All right, and then as like I said, time. Everybody's familiar with time and the second. So here are the prefixes that I was talking about. So the biggest takeaway you need to take from this is if I go up in size, okay, so say I go from meter to kilometer, right? A meter, make sure, let me get y'all just on me for a second. Oh, not there, hold on. Transition. Okay, so when I'm going from meter to kilometer, okay, right? So let's do centimeter to meter because I can probably do that with my hands. So a centimeter is this, a meter is this, okay? So it's 100 centimeters in a meter. All right. If I'm going from something smaller to larger, the actual number needs to get smaller. Okay? What does that mean? Let me pull up my paint pad real quick. Okay, so say I have let's say 1 centimeter is equal to 0.01 meters. Okay, so that's my conversion. Let me also say 100 centimeters is equal to 1 meter. Yeah, that'll do. Okay. So now so 1 centimeter is equal to 0.01 meters. If I go up in size, so this is a centimeter. Centimeter is smaller than a meter, right? And just think about what question they're asking you. Say they give you, I don't know, 5.76 centimeters, and they say how many meters. Okay, so I'm going to come back to myself for just a second. Remember, a centimeter is larger than a meter. If I go up in size, I have to go down in number. Okay, so I'm going from a centimeter to a meter. I'm going up in size, so my number has to get smaller. Okay, How much smaller? That's when I look at my board here. Oh, I lost it. Okay, so let's look for centi versus the base unit. So it's 10 to the negative 2 or 0.01. Alright, now you need to figure out, your job is going to be essentially how to figure out how to use that 0.01 to figure out the right value. Alright, let me go back to paint. Alright, I always say that a lot. You'll have to excuse me, I don't know why I get hung up when I'm doing these math problems. I say, alright. Okay. 5.76 centimeters. Remember, it's smaller, and I'm going from a smaller unit to a larger unit, so my number has to get smaller. And it has to get smaller by 10 to the negative 2. So that's 1, 2, that'd be 0.0576. Okay, so the 10 to the negative 2, I've moved it 2 spaces to the right. Alright, and if I wanted to check, I'd just say, well, I should have put that in front, but make sure y'all can still see this. Yeah, okay. So, if I wanted to check, I just go through what I just said again. So, smaller unit to larger unit means it has to go smaller in number. Do I go smaller in number? Yes, I do. Alright, so that's kind of how I keep track of which way I need to go. Okay, now if I'm going from a larger unit to a smaller unit, I have to get larger in number, and that's what you see going on here with the meter and the centimeter. The meter is larger. Let me do this one here. So say we want to go from 0.562 meters equals how many centimeters? Okay, I'll do millimeters this time so we do something different. Alright. So 562 meters is how many millimeters? First thing I want to do is figure out whether or not my number is going to be larger or smaller than the first one they gave me. So the meter is big, the millimeter is very small, so if I'm going from something large to small, the number has to go from small to large. Okay, the number is going to go the opposite of the length. Alright, so that means this has to be a much larger number than 0.562. So now I go to my little table here, and I see what the milli is 10 to the negative 3, so that's 3 places I need to move my decimal. And since I'm making this number larger, I'm going to move it to the right. So decimal goes right to 1, 2, 3. It would be 562 meters, millimeters, excuse me. Okay, so that's kind of my rule of thumb for doing the prefixes. Smaller in size, bigger in number. If it's bigger in size, it's going to be smaller in number. Okay, so that's how I do my conversions. Like I said, I want to get my iPad going back so I can just do it with my little stylus, and it makes it much easier. It's much more like a whiteboard. If I can't get it figured out by the time we start doing the next math, I'll hook up my actual whiteboard and set up a camera so we can do that off to the side here. Alright, so I apologize. I'll try to get better at that by next week. Okay, so this is going to go through each individual base unit. Remember, we talked about length, mass, volume, time. So this is just going to go through each one and explain to you that the length is measured in meter, and then these are the most common ones we use. Mass is measured in gram. These are the most common ones we use. These are how you convert it. Volume is measured in liter. Kiloliter, milliliter, or regular liter is pretty much all you're going to see. One thing I do want to mention about the volume, though, let me see what y'all are looking at. Yeah, so you hear people talk about cc's. Hey, let me get 50 cc's of that, or 200 cc's of this in a hospital environment or medical environment or scientific environment. A cc is a cubic centimeter. So when we talk about volume, remember back in your like early, geometry classes or whatever, and we did area, and we did the area of a box is the length times the width, right? Well, in volume, same as you did in geometry, it's the length times the width times the height. Okay, that is 3 dimensions. So a cubic centimeter is the length times the width times the height of a centimeter deep, a centimeter long, and a centimeter wide, and that's a cubic centimeter, and that's actually equal to 1 milliliter. Okay, so the units for volume are interchangeable with the 3 dimensional units for length. Okay, remember we talked about meter as a unit for length? Well, if I have 3 dimensions of length, I've created a volume, and thus I can use milliliter as well. Okay, so just kind of keep up with that. If you see cubic centimeter, it's talking about volume, not length. Okay, because it has 3 dimensions of length, so it's telling you about a space. Okay, and remember, volume is anything that in within a given space. All right, back to this. Let's see. And these are just some common conversions, and I will wait to do those till I can get my computer program or my whiteboard working, because I want to show you how to set up factor conversions, okay, and how to set up your math problems so that you can cancel things out and make sure you always come up with what you want to come up with, okay, and you don't get the denominator and the numerator backwards or whatever. Okay, so that's all coming up next week. I've spent almost at an hour now. A lot of today was an introduction, and I've still got this phone blowing off the hook in the background. My grandma's screaming. I apologize if y'all heard any of that. Um, Trying to get everything sorted out first week of the class. I'm going to have all these kind of problems, but anyway, if you have any issues with anything that we've gone over here, or getting into ALEKS, or what's on Cougar View, email me. I'll get back to you as soon as possible. The For my course, this section, Chapter 1A, Part 1 of Chapter 1, is not due until next Sunday, August the 29th. So you have plenty of time to kind of get in here, get familiar with the program, do your tutorials, your knowledge check, and get started on your objectives. Okay? So that's it for me. I will see y'all next week. Bye.